So I want to sort of, we've been working with vector spaces. We've been developing a framework for talking about solutions to systems of equations, and let's actually look at why that was needed for going forward. So let's go ahead and look at a second order differential equation, linear. So let's look at solving the equation y double prime plus y equals 0. Okay? So we'll talk more about this as we go, but we saw last time a lot of times, well, we saw last time we saw often for these we had e to some power was the solution. Okay, that's not going to be the case with this one. How come? Well, we want a function, so when we take its second derivative, the second derivative essentially cancels out with the original function. And that wouldn't happen with an e to a power necessarily. So what type of function do you think would work here? Do we have a guess? Some function that when we take the second derivative, we're back to where we started, but with a different sign.
Cosine or sine?
Yeah. So let's first take a guess. And we're going to guess that y equals the sine of t as a solution. Okay, so let's check that. So we get y prime is the cosine of t, and then y double prime is minus the sine of t. So I'm not going to write it out. Can you confirm visually that this checks? You guys feel good with that? So check. Okay, that's one solution. Okay, let's take a second guess here. Everything worked just fine for sine, and I heard somebody say cosine might work as well. Let's just check that. So if we took the solution, in fact, let's number that y1 and let's call this one y2. So if we took y2 is equal to the cosine of t, then y2 prime would equal minus the sine of t, and then y2 double prime would give us the cosine of t, and give us minus the cosine of t, and you can check that visually. It works in the system. Okay. So, and frankly, we had a couple of problems like this way early on in our chapter 1 notes, chapter 1 notes. So we've said that S, and I'm going to put a little bar there. I'm not very good at drawing that yet. Put an S with a slash down the side. The set of all solutions to an nth order linear homogeneous ODE is a what? So this was one of our examples when we introduced these topic. And you can kind of take a guess based on the way I drew that with that bold face. What's that?
Vector space?
It's a vector space. The set of all solutions is a vector space. Okay? So we want to show that this set right here, S equals to the sine of t comma the cosine of t, forms a basis of S, the set of all solutions. Okay. Before we can do that, we need the big existence uniqueness theorem for linear ODEs, because we're going to have to rely on that. Okay, so that's what we're going to show. We're going to take some time, go off and show that, and then we'll come back to solving these second order ODEs. But to do that, Everyone get that? Is it too far? Too fast? Okay. To show that, we need our existence uniqueness theorem for nth orders. So theorem, you can call this the existence uniqueness for nth order linear ODEs. Okay, notice I'm not saying that they have to be, yeah, I'm not saying that they have to be, am I saying they have to be homogeneous? They do have to be homogeneous, sorry. Homogeneous. ODEs. I'm not saying that they have to have constant coefficients, which is what we're going to sort of restrict ourselves to for a little while. Okay. So it says that the IVP, which would look like y sub n of t equals p naught y plus p1 y prime plus dot 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 plus p n y sub n minus 1. So that's the nth order linear ODE. And on the left-hand side, you get the nth derivative. On the right-hand side, you've got all the lower order derivatives and their coefficient functions. It's linear because the coefficient functions are all, each one of these is a pi of t. It depends only on t. So what else do we need? If it's going to be an initial value problem, we need some initial conditions. Okay? And in fact, for this to work, we need to have n of them. So the n initial conditions are that y of t naught equals y naught, y prime of t naught equals some y naught prime, comma, dot, 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 comma, yn minus 1 of t naught equals some yn minus 1 naught. Okay? So this is the nth order IVP, and we're saying that this will have a unique solution. This has a unique solution provided, or let me not say provided, that's a little misleading. Let me just say if P naught, P1, Pn are continuous. I'll just add, I should have put it in there, but let me just add, this exists on some interval containing T naught. So you're not guaranteed that the solution will exist, just like we had with the card existence theorem. It's not necessarily going to exist forever, but you can find an interval for which you can get a solution. Okay. Everyone get that? Okay. So let's return to our system. Okay, let's say x1 of t equals sine of t. This solves the initial value problem, x double prime plus x equals 0, with x of 0 equaling 0 and x dot of 0 equaling 1. So I'm using the dot notation here. What does that dot notation mean again?
Respect t.
Yes, yeah, so they're derivatives. Each dot refers to a derivative with respect to time. Yeah. All right, so that's, and in fact, not only does it solve it, but it's also what? So I'm saying that this this equation right here solves this initial value problem. Are there any others? Any other functions that would solve that initial value problem? No. So the cosine will solve, like we saw, cosine will solve the ODE, but it won't satisfy the IVP because of the initial conditions. Right? Yeah, it's a good. Yeah, let's make sure we clear the air on that. Okay. So before when I was just considering, I used y, but we were looking at y double prime plus y equals 0. We said, hey, sine of t and cosine of t both solve that, right? They solve the ODE, but not the IVP because you've got to also satisfy the initial conditions. So in fact, if I found one solution, the theorem on the previous page doesn't say that this has a solution. It says something even stronger. This IVP has a, oops, that was supposed to be, this IVP has a unique solution, right? So not only does sine of t solve this IVP, but it's also the only solution. Okay. And x2 of t equals the cosine of t. What does it solve? What IVP does it solve? Yeah, where x of 0 is 1 and x dot of 0 is 0, and that's for the same ODE. Okay. So So remember, we're trying to we're claiming that this pair of solutions is a basis for the vector space of all solutions. So now all we need to do is, well, not all. What we have to do is show that this thing is a basis. So what were the two things we had to do to show this was a basis?
Scalar multiplication and additive property of some sort.
So let's be careful of that. So showing that it was closed under vector addition and closed under scalar multiplication was what we had to do to show that it was a subspace.
Okay.
So and by subspace we mean like, well, in fact, what are you referring to when you say it is closed? Because it is closed under vector addition and it is closed under scalar multiplication. What are we talking about when we've got these two functions? What is the subset that we're talking about? So it's okay, we're practicing this vocabulary, we're learning the span, right? So we already know that the span is a subset. We don't have to re-show that it's going to be a subset, okay? But we want to show that the span of this. What's that?
Is it unique solution or because like determinant of because I remember the determinant of a does not equal 0, so that's the unique solution.
Okay, so we're gonna need something like that here at some point, yeah. So one way to look at it, these are two vectors, right? And I'm saying from these two vectors, what can you do? You can get to all the other vectors in the space of solutions. So I have to show, so we need to show that x1, this set right here, x1, x2, spans the space of solutions. That's the first thing we have to show. So if I've got a pair of vectors and I'm claiming that they're a basis for the entire vector space, I need to show that one, you can get to all other vectors from there. So it spans the entire space. And what's the second thing? So this shows that you can get to all other vectors, but what maybe I could get to all the vectors just from.
That they're linearly independent.
Yeah. So just because this is a spanning set doesn't mean it's a basis, because it might be that just having x1 or just having x2 would also span the whole thing. So I have to show that they're linearly independent. So we need to show that that it spans S and is linearly independent. So these are the two things. So if you go back and you look at our notes when we gave the definition for a basis of a vector space, we said it had to span it, and the set had to be linearly independent. Put another way, it's the minimal set that will span it. If you take one element out, you'll no longer span the entire space. Okay? All right. So let's start off with showing that it spans. Okay? So let's number those. So we call that 1, and we'll call that 2. Okay? So let's do 1. Okay? So how do we show that a set will span an entire vector space? Well, pick an arbitrary vector in there, right? And show that you can get there through some sort of linear combination. Okay? So let's let x of t be another solution to x double dot plus x, plus just x equals 0. Okay? So we're picking another vector in there, and what do I have to show? So again, you know, use this, when we're dealing with a very abstract vector space, but use R2 as an example, right? So here's a vector, and I'm claiming that, you know, maybe this vector plus and this vector form a basis. What do I need to be able to show? It's possible to do some sort of what to get to this vector? Addition and scalar multiplication, what do we call that? A linear combination. So there's got to be a way to get to this vector here with some linear combination of these vectors, which would be maybe go out this far along this one and go back this far along this one. Add those two together and you get to that vector. Okay? So that's what it, I mean, we got to see it all in two space in that nice sequence of videos, but now we're doing this very abstractly, but the answers are still the same. Okay? So we need to show that x of t can be written as c1 x1 plus c2 x2. Okay. Well, let's first say c1 x1 plus c2 x2 solves x double dot plus x equals 0 for all c1, c2. Why? There's two viewpoints you can pick to say why that's the answer. So first, I'm not saying that c1 and c2 equal x of t yet. I'll get there. But first I'm just saying that these two together solve this differential equation. There's two words you could use. Well, sorta. So we've already said that this is in the span, right? C1 x1 plus c2 x2 is in the span of x1 x2. Right? And what do we know about vector spaces? This is what you were saying earlier, Jalen. What property do they have? What's that?
Addition and scalar multiplication.
So they're closed under addition and scalar multiplication, okay? Which is a vector space. I.e. closed under addition and scalar multiplication. Okay, that's one viewpoint. Okay, that's the new viewpoint that we've taken. But in fact, we said this a long time ago. Given two solutions to a homogeneous ODE, any linear combination of those two solutions is also a solution by a principle called superposition. Okay, so that's one reason why it's true. The other reason why it's true is superposition, which is something we talked about early on. So this is the differential equation view, and this is the vector space view. Okay, so there's either viewpoint works. Okay, this had to do with the differential equation being the derivative being a linear operator, and we showed that for linear operators, the sum of two solutions will also be a solution to a homogeneous equation. Okay, so that's two viewpoints. So any linear combination is a solution. Okay, then we need to show that this solution also satisfies the same IVP that this one does. Okay, so suppose, and this part's not going to be clear, I think, until we get to the end of it. But suppose so this is the solution, that x of t naught equals x naught, and x prime of t naught equals x naught prime. Okay. We want our linear combination c1 x1 of t naught plus c2 x2 of t naught to equal x naught, and we want the derivative of our solution, c1 x1 of t plus c2 x2 of t, evaluated at t equals t naught to equal this x naught prime. So put another way, we've got these two equations we want to satisfy. We want c1 x1 of t naught plus c2 x2 of t naught equals x naught, and we want c1 x1 prime of t naught plus c2 x2 prime of t naught to equal x naught prime. So what I'm saying from a differential equation standpoint is we want to show that this linear combination here, solves the exact same IVP. Okay? So what do we have to do? We've got to find constants so that it solves this IVP, and that's what I'm setting up here. Okay. So this looks like we could rewrite this in a matrix equation as x1 of t naught, x1 prime of t naught, x2 of t naught, x2 prime of t naught, times c1, c2 to equal x naught prime. So I want to prove that there's a solution to this equation. That is, I want to prove that I can find C1 and C2 so that it solves the same IVP. So I've got a whole bag of tricks that I could use. Okay? To show that a solution exists, to either the system, if you're thinking about it like up here, or, sorry, this should be 2, that's the whole system, or the matrix equation, which is how we're looking at it here in red. Okay. We've got a whole bag of tricks now that we could do. Okay. For example, we could show, if I go ahead and call this this expression right here A, I could show that A row reduces to what? The identity matrix. If it row reduces to the identity matrix, then this system has a unique solution. Okay? What else could I show? I could show that A has n pivot columns. I could show that A inverse exists. And there's one other one that's probably going to be the best choice in this context. Actually, there's several other ones we could still do, but which one, I'm not going to list any more other than number 4. What's one other thing we could do? So Jack, this is what you were saying earlier, I think.
Yeah, the determinant doesn't equal 0.
Yeah, we can show that the determinant is not 0 for all t. So let's do that. I think that's easiest. So the determinant of x1 prime, x1 of t, x1 prime of t, x2 of t, x2 prime of t. Let's compute this determinant. Well, here we're actually, let's go back to the real world. What are these equations? This is sine of t, whose derivative is cosine of t. And this is cosine of t, whose derivative is minus sine of t. And let's compute the determinant of this. Okay, usually computing determinants is a whole chunk of work, right? But this is a nice 2 by 2. Okay, so we can use that trick. That, in fact, I'm trying to think, you guys are on 3.5. We've already done that trick. You did that in your homework to show a shortcut for calculating these determinants, right? It's this times this minus this times this. Okay? So we get minus sine squared of t minus cosine squared of t, which gives us a negative sine squared t plus cosine squared t, which gives us negative 1. So because that's true, because the determinant isn't 0, we're able to find constants c1 and c2 so that this linear combination of them solves the exact same IVP as our arbitrary vector in the vector space. Okay. So let's just say that. So c1 x1 of t plus c2 x2 of t solves the same IVP as x of t, i.e. it solves x double prime plus x equals 0, x of t naught equals x naught, and x prime of t naught equals x naught prime. Okay. So what are we trying to do? We picked this arbitrary vector here, this arbitrary solution. Okay. To sort of classify it, we went ahead and found out what initial conditions it would have satisfied. And then we found a linear combination of these two so that we could get a solution to the ODE and it satisfied the same initial conditions. Okay. So both of these solve the same IVP. I claim now that they're equal. Why are they equal to each other? How do I know that's not, just two completely different functions that just happen to solve the same IVP? And this kind of goes to the same mistake we had earlier. So if they solve the same IVP, by the existence uniqueness theorem, they must be the same function. Because the existence uniqueness theorem says not only is there a solution, but if you have two solutions, they must be the same thing. Okay? And by the existence uniqueness theorem, x of t then is equal to c1 x1 of t plus c2 x2 of t. Okay? That's really interesting. We used, to prove that we could find constants c1 and c2, so that the two would equal any other solution we came up with, we went ahead and created a system of equations and then said that system of equations has to have a solution because the determinant is never 0. Okay? All right. Okay. So what have we shown? We've shown that the span of x1, x2 is equal to our vector space. We've just shown that our spanning set spans the entire space. It's the set of our solution, the set of those two vectors spans the entire space. Okay. What else do we have to do to show that it's a subspace? Or excuse me, what else do we have to do to show it's a basis? Excuse me. What's that?
Oh no, I was being enclosed under.
If it was, yeah, my question was subspace, that was
That's
it,
a
yeah.
subspace.
But if we want to show that it's a span, or excuse me, if we want to show that it's a basis, we have to show that it spans and that they are linearly independent, okay? Let's show x1 of t and x2 of t are linearly independent. There are a few different ways to check for linear independence. Okay. The way I want to do it is, because this is how we'll usually do it going forward. Okay. The easiest way here is to check the Wronskian. That's what we introduced last time. So let's look at the Wronskian of x1, x2. So what was the Wronskian? It was an n by n matrix where n was the number of elements in that. So there's x1, there's x2, and then we take up to as many derivatives as we need to create a square matrix out of this. So we get x1 prime, x2 prime, and what does this determinant come out to be? We've already done it. It comes out to be -1, which is never 0, which does not equal 0 for all t. So this set right here, x1, x2, is a basis for the solution space. Meaning, the general, so here I'm going to go ahead and say it, the general solution to x double prime plus x equals 0 is this equation right here. Or what did we say x1 and x2 were? It was the sine of t plus c2 cosine of t. So I tried to keep, what we were doing was actually basically the proof. I just every once in a while showed you what these actual functions were, and we actually had a differential equation that we were looking at. But let's just note this idea extends to nth order linear non-homogeneous ODEs. So specifically, what we've said is the solution space for an nth order, I need a shortcut for writing this, I don't want to have to write this every time. Nth order linear non-homogeneous ODE, so let's just put L and O, I guess. We'll repeat that as L and O. For a linear non-homogeneous, or excuse me, linear, I said non-homogeneous, it should be homogeneous. sorry folks, this whole thing's for homogeneous, right? We set it equal to, where did we do that? We set it equal to 0. Okay. So the solution space for an nth order linear homogeneous ODE, okay, has dimension what? So the dimension is the number of vectors it takes to span it. So when we had a second order ODE, it took 2 vectors, and we just showed all that work, just also showed this. So it has dimension n. So any collection of n linearly independent solutions is a basis. Okay? So let's look at an example now. Let's just go straight to the answer for this. So give the general solution to y double prime minus 2y prime minus 3y equals 0. All right, so if I want to give the general solution, this is a second order, so I need 2 solutions. Okay, I'm going to go ahead and give you those 2 solutions. We'll show that we've got the general solution, and then I'll show you how I found those 2 solutions. Okay, so y1 equal to e to the minus t solves this ODE. Okay, check that. So when we take the second derivative of this, we've got an e to the t, right? Because of the 2 minus signs. Then this would be minus a minus 2 e to the t, so that gives us a total of 3 e to the minus t's, minus 3 e to the minus t. Does everyone see that that solution works? Or do you want me to check that? We're okay? You sure? Okay. A second solution is e to the 3t. Okay, let's just check that one. So notice that y2 prime is 3e to the 3t, and y2 double prime is 9e to the 3t. Plugging those in, that gives us 9e to the 3t minus 6e to the 3t minus 3e to the 3t, and sure enough, those all cancel. So, I have 2 solutions, right? Is that enough to say that this is a basis? What do I still have to show? Yeah, I still have to show that they're linearly independent. Okay? So we have 2 solutions, which is the dimension of this vector space, right? The vector space of solutions is dimension 2, so we've got 2 of them. We're good to go as long as we show that they're linearly independent. Okay? So we have 2 solutions. If they are Li, then they are a basis. So as Tony said, what's the best way to check that they're linearly independent? We're going to take the Wronskian of them. So we've got the Wronskian of e to the minus t, comma, e to the 3t. So let's check that. That's e to the minus t minus e to the minus t, and e to the 3t, and then 3e to the 3t. So taking the determinant of this, we end up with 3e to the 2t, 3e to the 2t minus, so plus 3e to the 2t, which gives us 6e to the 2t. Can this ever be 0? It's the exponential function. When does the exponential function output a 0? Never does, right? Which is never 0 for all t. Okay. So that means that we've got our two solutions. We've just checked that they're linearly independent. 2 is the number we need to span our set as long as they're linearly independent. Okay. So what was our differential equation? It was y. So y of t equals c1 e to the minus t plus c2 e to the 3t is the general solution. Okay. Questions on that, folks? All right. Well, I think there should be one question. I gave us two solutions and we checked to see that they worked. What should your question be? Well, yeah, I'm thinking, how did he come up with those two solutions, right? Okay. So if you've got two solutions, we now know a way to, or if we've got two things that we think are solutions, we know how to check to see if they work. Let's check to see if they're a basis, but let's go ahead and do this again. Okay. So now let's solve this same thing, y double prime minus 2y prime plus 3y equals 0. Okay. So we're just going to take as a guess that a solution is going to look like e to the RT. Okay. That seems like a good guess. It worked for linear, it worked for the first order ones. Now, some second orders have sine and cosine as their answer. Some have e's, some have some sort of combinations of those. Okay. We're going to learn as we go to figure out which one's which, and I'm going to start giving you kind of a checklist, a method for doing this. But let's go ahead and just see if y equals e to the RT will work. Okay. Let's just check if y equals e to the RT works. Okay. So its first derivative is re to the RT, and its second derivative is r squared e to the RT. Okay. And we're only going to have to do this one time. I might do it one more time just to reiterate it, but when you guys are doing your homework problems, you'll just jump to what the big result is here. Okay? So we substitute these in, and we end up with r squared e to the RT minus 2r e to the RT plus 3e to the RT equals 0. So each one of these terms in here has a factor of e to the RT, so we can factor them out. And we're left with r squared minus 2r plus 3 equals 0. So let me give you the name for this. We're going to call this thing right here the characteristic equation. Okay. Now, what I'm saying, when you don't have to do this every single time, could you figure out what the characteristic equation is without positing a solution? Yeah, it's just simply you'll have an r squared term here, minus 2r term here, and then a constant term here. If you do, we'll do this one more time just to reiterate how it works. But you will usually just, given a nth order linear homogeneous ODE, you'll go straight to the characteristic equation for it. Okay. So because I've got two factors equal to 0, either e to the RT equals 0, but when does that happen? Never. Or r squared minus 2r plus 3 equals 0. So I can solve this equation by, in this case, by factoring, but it's a quadratic equation, so I've got all the tools from algebra. So we get this factors as r minus 3 times r plus 1 equals 0, which gives us r equals 3 or r equals minus 1. So as long as r is one of those two values, then e to the rt will be a solution. So y1 equals e to the 3t, and y2 equals e to the minus t are both solutions. Which is now we're back to where we started, this problem. Okay? So that's how I got those two solutions, was using the characteristic equation. But the work that we've been, I mean, we could have shown this step before we did chapter 3, but how would we know that all solutions can be written in this form? Right? We wouldn't know that all solutions can be, so our general solution, y of t equals c1 e to the 3t plus c2 e to the minus t. How do we know that all solutions can be written this way? Because we know that those two vectors span the entire solution space. Questions on that? All right. So one more time, I just want to reiterate, we found two solutions and we showed they were linear independent. That was enough. The first time I did this, what did I do? I had to show that it spanned, right? But that same work would always apply. Okay, so there's no reason to revisit that work. So because we know, or put another way, because we know this is a second order ODE, it's the dimension of the vector space is 2. So once you've found two linearly independent solutions, you're done. You can write that then as your general solution. Okay? So what if this was a third order ODE? What do you need to do? What's that? You need to find 3 solutions and do what? You have to confirm that they're linear independent, and then you can give your general solution. You're done. Okay. Good. Okay, so let me do one more. I'm going to set this up for you. Because I went ahead and gave you some of these in your homework. So let's consider y double prime plus 6y prime plus 9y equals 0. Okay? What's the characteristic equation of this?
R squared plus 6r plus 9.
Yeah. So it has characteristic equation r squared plus 6r plus 9 equals 0. Let's find the roots of this characteristic equation. So this factors to be r plus 3 quantity squared equals 0. So we get that r equals -3 is the only root. And this root has multiplicity 2. Okay. So what's the issue here? See what the problem is? What's that?
There's only one solution.
We've only got one solution, right? I can't claim, don't write this down. I can't claim y1 equals e to the minus 3t and y2 equals e to the minus 3t, and that the sum of those two will span my entire vector space. How come? Because they are the most linearly dependent pair of solutions you could come up with, because they're the same thing, right? They're the same solution, so they're certainly linear dependent. They're not linearly independent. And you could, if you really wanted to, you could take the Wronskian and show that it's always 0. Okay? So that's not going to cut it. Okay? So we know y1 equals e to the minus 3t is one solution. We need another. Okay? I'm not going to do this because we're gonna show the work for this in section 4.5 and section 4.6. So if you remember, we introduced a method. We've introduced a couple of methods for, hey, given one solution, how can we find some other solutions? And one thing you could start doing is just multiplying this by some other function, okay, and check to see what would work. Okay, and it turns out y2 equal to te to the minus 3t is also a solution. Okay, I'll let you check this on your own time, just because I want to keep moving through this. Okay, so I'll let you check that. Okay, but you sort of, I mean, you'll have to do the product rule, right? When you take its derivative, and then when you take the second derivative, you'll have to do another product rule. Okay, and then substitute everything into the ODE. Right? But do you guys feel pretty comfortable doing that? Checking, okay? So it's a solution, and I'll let you check that. Okay? So now we've got two solutions, and what do we need to do?
Make sure they're linear independent.
As long as they're linear independent, we're done. Right? So now let's compute the Wronskian of y1 and y2. Okay? Well, that is e to the minus 3t and minus 3e to the minus 3t. When we do the second one, we've got te to the minus 3t, and here we've got to do a product rule, so there's minus 3te to the minus 3t plus e to the minus 3t. And when we take the determinant of this, let's see here. When we multiply the first here, we'll get minus 3t plus 1. Because the e, oh, no, those aren't different factors. E to the, there's a minus 6t. E to the minus 6t plus e to the minus 6t. That's when we do those two. Minus, and then when we do this, we get minus a minus 3t e to the minus 3t. So this just cleans up to be e to the minus 6t, and for what values of t is this 0? It's never, okay? Which does not equal 0 for all t. So, since the Wronskian is never 0, then we can go ahead and say that these two solutions are linearly independent. There's no way to create one of them by doing some sort of crazy multiplication to the other. We've got two of them, and we were solving a what-order linear homogeneous ODE? Second order, so we're done. We've got as many independent vectors as we do dimensions to our vector space, so it's a basis. So y of t equals c1 e to the minus 3t plus c2 t e to the minus 3t is the general solution. We know that spans the entire vector space.
It's going to be the same thing with most of the, we call it a characteristic, when we end up with like a dual, just kind of like what we did right now. We're just going to add a t.
Yeah, so that's a general strategy that will carry over to some other things that we do. Okay, adding more powers of t is often a strategy that we'll do. Yeah. Now, we're actually almost done with all nth order ODEs, because why? The fundamental theorem of algebra says that every algebraic equation can be broken down into either quadratics or linear functions. And we've learned how to handle all of those. So we could always give the roots this way. The issue we have to deal with is what happens when we have repeated roots. that's what we just dealt with. And then we have to deal with what happens when we have complex roots, and that's going to be my last example. Okay? So in summary, if AR squared plus BR plus C equals 0 is the characteristic equation, if B squared minus 4AC is greater than 0, then you get two roots, R1 and R2. R1 and R2. And for the second order then, we'd have y of t equals c1e to the r1t plus c2e to the r2t. Is the general solution. Okay. What else have we learned how to handle? Well, we've learned how to handle the case where you've got repeated roots. When would that happen? So I'm sorry, you guys remember that I didn't reintroduce this. You guys remember this guy from algebra? We call that the discriminant. If the discriminant, that's the thing that shows up under the radical in the quadratic equation. If that is positive, then you get two real solutions, right? You get two real roots to your quadratic equation. And if that's the case, those two real roots, and I didn't say this, but because it's positive, that means those two real roots are distinct. And every time you check for linear independence, that will always happen with these E functions. So that's the general solution if the characteristic equation has two real roots. Okay? If b squared minus 4ac is equal to 0, then you get one repeated root. Okay. And y of t, this is what we just showed, c1e to the rt plus c2 t e to the rt is the general solution. Folks, it took us a long time to set up all these dominoes, but I think things are kind of falling fast now. Okay? As our ability to solve, we can now solve quite a lot of these second order linear homogeneous ODEs if they have constant coefficients by looking at this characteristic equation. Okay. All right. By the way, our book puts the situation, he breaks it up into two different sections, or actually, so I'm kind of covering three sections at once right now. Okay. I'm introducing the second order problem. We just looked at the case where we have real roots to our characteristic equations. In a moment, we'll look at the case where we have complex roots. Those are sections 4.1, 4.2, and 4.3. So I want to kind of cover the whole spread of them tonight, and then next class period we'll go in a little bit more detail for some of the other things that we're missing as I skip through these sections. Okay.
So right now we are going to deal with nth order, so it could be like third order, fourth order, and we're just going to have to break it down to.
Yeah. So let's see here. Let's just give ourselves a real easy one, just so I could show you that. So yeah, for Tony's question, let's say we had y4 is equal to I need something that factors by grouping. So let's see here, x squared plus 2, that's something plus 2, x squared minus 4 times x squared minus 9. So if we had is equal to y triple prime minus 9 minus 13 y double prime plus 36y. That was our differential equation. Then we just need to find all the roots to the characteristic equation. Was I missing one there? I don't think so. So let's go ahead and set up our characteristic equation to be r cubed minus 13r squared plus 36. Well,
36R?
I don't. No, I don't think so. Okay. Let's just see. Let's just see. Does this thing factor to be? What am I doing? I don't know if I'm ready to do this. Sorry, guys.
We could skip it too.
So the point being is let's just suppose suppose this is y triple prime plus b y double prime plus cy prime plus d, and it has roots. Well, it has ar squared plus b, or ar cubed plus br squared plus cr plus d as its characteristic equation. With roots R1, R2, R3, it has these 3 roots. I feel like I'm missing something here. Sorry, this should be to the 4th. This is, you were right, Jalen, I'm sorry about that. That should be AR to the 4th. That's what I'm missing. I'm missing a dy. That's what I'm missing. Okay. AR to the 4th plus BR cubed plus CR squared. I'm sorry. I'm not ready to do this.
No,
Sorry.
you're good.
Sorry. I'm confusing myself. I apologize. Anyway. Yes, so basically, once you've got the roots, if they're repeated roots, you're going to do what we just did, okay? But the roots would only be repeated so many times. Or if they're all distinct roots, then you could just add up each one, easily, and that would give you the solution. Okay? The only case that we haven't looked at yet now is the case where we have complex roots. So let's jump into that. Okay, so I want to jump into that, but I also want to do it by way of a story problem. So it's going to take us a little bit to get into the solving the equation. Okay. So we call mx double prime plus bx prime plus kx equal f of t a harmonic oscillator. So let's just say this does a few things. This models springs, simple pendulums, and LRC circuits. We'll get to the LRC circuits next time, next class period. Okay. So let me just say if it just looks like mx double prime plus kx equals 0, this is called a simple harmonic oscillator. If we have mx double prime plus bx prime plus kx equals 0, then this is called a damped or dampened harmonic oscillator. And then if we have mx double prime plus bx plus kx equals f of t, with f of t not 0, then this is called a driven harmonic oscillator, or a driven. So this model actually encompasses a wide variety of physical phenomena. We'll worry about simple pendulums. By simple, I mean pendulums that don't swing over the top. They can only swing back and forth like this. The model breaks down if it can swing over the top. So this will model simple pendulums, and we'll pick up on LRC circuits next time. We'll actually do an example of that. But let's talk about this in terms of springs. Okay? So if you take and release a spring, it's going to oscillate back and forth. It's got this restorative force here that's due to Hooke's law. Okay? If you want to take into account some sort of air resistance or some sort of friction, then you've got this dampening force here. Okay? So this is the dampening force that would eventually, if the dampening force is, if the B value is positive, it's eventually going to bring this spring down to a halt. It's eventually stopped. That's assuming you don't have an external driver. So an external driver might be you've got a spring hooked up, but you've also got a motor that every once in a while does a revolution to keep energy being inputted into the spring, and it continues oscillating. Okay? So if you have a driving force, then it's a driven harmonic oscillator. If you have a dampening force, then it's dampened. And then if you have neither of those, then we'll call it a simple harmonic oscillator. Let's explore that just a little bit more. Okay. So here's the picture that can always work. As long as if m is greater than 0 and b and k, actually let's just say all three of those are greater than 0. If m, b, and k are greater than 0, then the way we can look at this, you can always interpret a model this way, as you've got a spring affixed to a mass. So if that's all you have, and you assume that this situation is frictionless, then you've got the simple harmonic oscillator. Okay? So it'll oscillate back and forth. If you include a dampening force, for some reason, I'm not entirely sure why. I don't do physics, but for some reason, rather than thinking of there being friction here, we simulate friction by putting a sort of a dampening thing here, where we have, say, a piston that fits in this, and as it oscillates back and forth, you've got some sort of fluid in there that causes this to slow down. Okay? Does that make sense? It's not a very good diagram. If you want a better one, take a look in the book. Okay, so if I include this dampener, then it's dampened harmonic motion. And then what you could think of is, as you could think of there being some sort of let's see how to draw that. You could think of there as being some sort of piston hooked up to this thing, where this rotates about, and this would introduce an external force into this. Okay? Oftentimes, as I've just shown you, Oftentimes that external force we think of as being some sort of periodic function. Doesn't have to be, but that's usually what we think of it as being. So this is rotating, but there's also energy in the spring, so it's oscillating as you get these external rotations, providing more energy into the system. Okay, so that's what we have going on. So let's look at an example of this. So a spring requiring 1 Newton to stretch, 0.25 meters, is affixed to a mass of 1 kilogram. Dampening force of 0.5 newtons is experienced if the mass is moving 0.25 meters per second. So then we're going to add to that, the mass is released 0.5 meters to the right of rest. And by the way, is released from rest. When I say from rest, I mean motionless. When I say to the right of the rest position, I mean where the spring would naturally want to sit. So the word rest kind of meaning 2 different things in there. Okay. So let's go ahead and figure out our calculations to set up the differential equation. Okay. So there's the restorative force. Is given by FR, which is directly proportional, opposite in sign, and directly proportional to the distance stretched. Okay? So this was called Hooke's law. You've probably seen it before. Okay? Anyone not seen Hooke's law before? Great. Okay. So that's Hooke's law. So in our case, we had a restorative force. We said here in the preamble, we said, okay, we've got this force of 1 Newton to stretch at 0.25 meters, which means we're exerting 1 Newton of force to stretch it. So it's got a restorative force that's equal and opposite to that, right? So the restorative force would be -1, and that equals k times 0.25, and so we can, minus k times 0.25, and so we can solve for k, and we get 4 is our k value. Okay. To be honest, that's unrealistic. Well, probably unrealistic for a spring like what we're doing, but we want the numbers to work out decent. So, okay, so that's the restorative force. We use Hooke's law. Your k value should always be positive if this is a spring. Yeah, So the way I thought of this is this was negative because it was opposite the force that we were exerting to stretch it. Okay, so that's what caused our k value to come out to be positive. I would just say if you think k is negative, if you do the work and you get k is negative, just change the sign on it so that it's positive. Okay, that's the restorative force. The dampening force due to dampening is opposite and directly proportional to the velocity. And you've probably seen that if you guys have seen drag forces in physics equations. We usually have it being proportional to the velocity. Okay? So this is equal to -k times x dot. Okay? I don't think that's anybody's law. It's just nobody came up with that as a law. It's just stated. So in our case, we said that you'd have an opposite direction force of 0.5 newtons if this thing is sliding along the table, when it's sliding along the table at 0.25 meters per second. Okay, and I'm sorry, I used K there. I should use the letter B to be consistent and not confuse it with that other K. So B. So this would be then negative B times, it was 0.25. And so we get that B is equal to 4. Okay. Oops, I'm sorry, we get B is equal to 2. Okay. Okay. In this case, what's the driving force? What's our driving force in this case? Just in the situation that I presented. Well, there isn't one, so it's 0. Okay, so one of Newton's laws, I don't know. I think it's the second one. Is that F equals ma?
Mm-hmm.
Okay. Says that mass times acceleration is equal to the sum of the forces. Okay, and you guys have probably done more of this than I have. Well, in that case, then we have m x double dot is equal to your external force minus your restorative force minus your dampening force. Okay. So I'm in the process. I mean, this is how you would come up with that harmonic oscillator for this scenario. So if we go ahead and input 0 for our driving force function, and 4 and or 5 and 4 for K and B respectively, or I'm sorry, 4 and 2 for K and B respectively. Then we get the mass was 1, so 1 x double prime plus 2 x prime plus 4 x equals 0. And there's the differential equation for this system. Okay. So I know it's not very exciting that we're solving differential equations with constant coefficients, but this models this spring, the book calls it a dashpot, I hadn't heard that before, this spring dashpot system very well, even though it's not a very complicated differential equation. So here's our differential equation. We want to solve it. So what are we going to do? Oh, let's go ahead and, let's go ahead and give it as an IVP. So the IVP, real quick, would be x double dot plus 2x dot plus 4x equals 0, together with 2 initial conditions. We said that we released it 0.5 meters to the right of rest, and we said that we released it from rest, so we have that. So there's the IVP that goes with this. So what are we going to do to solve? We'll worry about the IVP part, the initial conditions, in a moment. How do we solve this differential equation?
Characteristic.
Yeah. So we're going to look at the characteristic equation here. So here's the solution. Okay. The characteristic equation is r squared plus 2r plus 4 equals 0. So if we go through to solve this one doesn't factor. Okay. So what could we do? Well, let's go ahead and, I don't know, pick your poison. I'm going to complete the square. You could use quadratic formula. Either way. So we get r squared plus 2r is equal to negative 4. R squared plus 2r, then I'm going to take half this term. You guys done this recently? Take half this term here, so half of 2 is 1. Square it and add it to both sides. And then on the left-hand side, we've built a perfect square trinomial, so we've forced it to factor this way. That's a negative 3. And what are we seeing that we're going to get for our roots to this characteristic equation? We're going to have imaginary roots. So we get that r plus 1 is equal to plus or minus the square root of -3, or r is equal to -1 plus or minus the square root of 3i. Okay. So the last piece of that pie when we were looking at the discriminant was, what do we do when we get a negative discriminant? Okay. So I'm just going to give you the answer now so we can have a solution to this problem, but then we'll spend some time looking at why that is the answer. Okay. So it turns out, it will be shown, I guess, that the solution then is x of t equals c1 e to the minus t times the cosine of the square root of 3t plus c2 e to the minus t times the sine of the square root of 3t. And what I'm saying then, so that's the solution. Is the solution. What I'm showing is if b squared minus 4ac is less than 0 for that characteristic equation, then your roots are we'll just say r equals some alpha plus or minus some beta I, right? When the discriminant's negative, you get two imaginary solutions. If that's the case, and we're going to show this here, that'll be the last thing we do is to show this. If that's the case, then y of t equals c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t is the general solution. This is by far the most complicated case. You've got complex roots to your characteristic equation. Okay. So, for our spring problem, we just said that x of t equals c1 e to the minus t cosine, was it 3? Yeah, it's cosine square root of 3t plus c2 e to the minus t sine square root of 3t is the general solution. What do I still have to do? What's that?
Solve the IVP.
Yeah, we got to solve the IVP, right? Okay. So we know that x of 0 equals 0.5, right? So let's go ahead and plug 0 in for t. That gives us c1 times the cosine of the square root of, the cosine of 0. Well, so do you guys see? So plugging in 0 for t, we'd have 0 as the argument of cosine, so we get cosine of 0 is 1. So this is c1 times 1. Plus, here we'd have c2 times 1, but then the sine of 0 is 0. So we just end up with c1 is equal to 0.5. We all okay with that? Okay. So what do I have to do next? That helped me find one of the constants. What do I have to do next?
Don't you have to differentiate?
Yeah, we got to differentiate this, right? And then take the derivative, okay? Or excuse me, differentiate this and then evaluate at 0.5. So let's see here, x prime of t would be, so here's my first times the derivative of the second plus my second times the derivative of the first. Okay, so So it's the derivative of the first term plus, now again, a product rule, so here we go, C2 e to the minus t, there's the first factor, times the cosine of the square root of 3t times the square root of 3. So it's my first root of the second plus the second times the cosine, or times the derivative of the first, which is minus c2 e to the minus t. So that would mean that x prime of 0 would be, so the first and last terms vanish, and so we end up with minus c1 plus c2, right? Is that what we have? Check me on that. Let's see. This term vanished.
Wait,
This becomes.
why does the first term vanish though if there's a C1 and a C2?
Oh, because this is all times this sign, and sine of 0 is 0.
Oh yeah.
Yeah. So that, because of this factor right here, the whole first term vanishes. This just becomes 1. That becomes 1. So we get minus c1. Yes, I think we're okay. And what do we know that this is supposed to equal? It's supposed to equal 0 because it's the initial speed. And we already said that this was 0.5, so we get that C2 is also equal to 0.5. So then that gives us finally as a particular solution to the IVP, 0.5 e to the minus t cosine square root of 3t plus 0.5 e to the minus t sine square root of 3t, and that's our solution to the spring mass problem.
It's faster if you just put it in a matrix, like 2 vectors.
Oh yeah, that might have been faster. Well,
I don't know.
You'd still have to. You'd still have to take the derivative, yeah. But in general, we saw this already back when I was trying to initially convince you to do systems of equations. Why we want this method is, for larger IVPs, you might have so many arbitrary constants that you won't be able to nicely solve this, or won't be able to quickly solve this.
Right.
And so, yeah.
You can't get rid of one of the constants in the first one.
Yeah, or if we're doing a third order where you have 3 constants, even if you could get rid of 1 or 2 of them.
Starting to make sense.
Yeah, cool. Okay, so that's the differential equations side of what we want to do. So if you look at the website, I went ahead and put the first chapter 4 homework, because again, I've covered the material from all 3 sections, but just at a quick skimming, okay? What we need to do is we need to go back and we need to be able to, okay, let's see if we can rearrange these equations. We're going to look at phase portraits. We're going to actually call these different spring systems by different names, if they're damped, if they're over-damped, critically damped, etc. So we're going to start working more with this. But as a first pass, here's your questions, okay? Most of these are just, so there's a few of them are story problems. This is a spring, this is a spring, this is a spring. And then the rest of these are just using the characteristic equations to solve some of these, okay? But I want to give you some practice with that. This one, I wasn't sure if I was going to get to the repeated roots example, so that's why I just mentioned that. But we got to it, so you should know how to do number 11 with the repeated roots. Okay, so that's what's coming up. That's what I want you to work on for your homework. Okay? So what I have left to do today is we've said, okay, in general, if the roots to your characteristic equation are alpha plus or minus beta I, why is this the solution to it? Okay. So that's what we're going to spend the last bit of time on. Okay. All right. So the first thing I want to do is I want to show Euler's formula. Okay. you guys remember Euler's formula? Yeah, so that's okay. It says that if you have e to the ix, that is equal to the cosine of x plus I sine of x. So I want to review this, why that's true. It's going to do a review of power series, which is something that we're going to cover in here, so we might as well do a quick review of this, just so you get, I don't know, when was the last time you guys looked at power series?
2 years ago.
Yeah, it's probably been a minute, so let's look at that. Okay, so we're gonna kind of get a review of power series by looking at proving Euler's formula. So recall, if I give you f of x equals e to the x, that this is a function that equals its power series representation, and its power series representation was what? Do you remember?
One over x squared.
Not quite. It was x to the n over, x to the k over k factorial. So that's its power series expansion. You guys remember that? Yeah, you can? Okay. Okay. What if I gave you sine of x? You remember what its series representation was?
That one's 1 over x or 1 over x squared, something plus something. Right?
No, I think you're thinking of 1 over 1 minus r, or 1 over 1 minus x. Yeah, I think you're thinking of the geometric series. Yeah. So this one is the sum from k equals 0 to infinity of -1 to the k, x to the 2k plus 1 all over k plus 1 factorial. Was that?
Totally remember that.
Well, I would encourage you to start maybe putting them on flashcards, because as we get to the power series representation portion of the course, you'll need to remember these three anyway, and maybe the one you mentioned just a moment ago. So then the cosine is -1 to the k, x to the 2k all over 2k factorial. All right. So this is kind of a nice summary of one of the uses of power series that maybe we don't see in our first passing. So let's look at e to the ix. E to the ix is the sum from k equals 0 to infinity of ix to the n, ix to the k, all over k factorial, right? What did I just do? I took, if e to the x that's its power series, then if I want to evaluate e to the ix, I just replace x with ix. Everyone okay with that? So this is something that will show up on one of your exams. It may be this one, and maybe when we get to the power series. So I think it's an important thing to be able to see, or be able to do. All right. So let's write out the first few terms of this. Okay? So when k is 0, this is anything to 0th power is 1. 0 factorial, I'll just write as 0 factorial. Okay? Plus ix over 1 factorial plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial. I need to get out to 5. I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial plus da da da. Okay, writing out the first 6 terms. Okay. I'm not going to, there was a very important idea that was taught in Calc 2 it's not always emphasized because you got so much going on. And it has to do with the test tests for convergence. Do you guys remember the phrase, so something could either converge or it could converge absolutely? Okay. That's okay. We'll review that when we review power series. Anyway, this series not only converges, but it absolutely converges, meaning that if you took the absolute value of it, it's still, of all the terms, it still converges, which is stronger than just regular convergence. When you have absolute convergence, this is an infinitely long series, right? We all know that you can interchange all terms of a finite length of sum, right? Like if I have 3 plus 7 plus 2, that's the same thing as 7 plus 2 plus 3. I can interchange those terms. It's not necessarily true for an infinite sum. But it is true if that infinite sum converges absolutely. Okay? So that means I can rearrange all these terms in this series. So what I'm going to do is I'm going to grab, who do I want to grab first? We'll grab 1 over 0 factorial plus I squared x squared over 2 factorial plus I to the 4th x to the 4th over 4 factorial plus dot dot dot. So I grabbed all of those terms. And then I'm going to grab all the other terms. So plus ix over 1 factorial plus I cubed x cubed over 3 factorial plus I to the 5th x to the 5th over 5 factorial plus dot dot dot. Everyone see what I did? I basically grabbed all the even powered, and that gives you a hint of what I'm doing. If you remember that cosine's an even function, sine's an odd function, that actually helps with this. I took all the even powered terms, collected them together, all the odd powered terms. How are we doing? Okay. So then, remember your powers of I? You guys remember how that goes? Need a review of that? So just as a reminder, I to the first power is of course just I. I squared was defined to be the number that when you square it you get negative 1. But a consequence of that is that if I write I cubed, I could think of that as I times I squared, right? Just by properties of exponents. But that would then be I times negative 1, which is negative I. So I cubed is negative I, etc. What we find then is I to the 4th power. You could think of many different ways, but maybe I squared times I squared, which would be negative 1 times negative 1, which is 1. And then it repeats. I to the 5th is back to I to the 6th is negative 1, I to the 7th is negative I to the 8th is 1, and it repeats itself. Do you guys remember that? Jogging that you got? Okay. Okay? So I'm going to go through and apply all those properties. So this becomes 1 over 0 factorial minus x squared over 2 factorial plus I to the 4th is 1. So x to the 4th over 4 factorial. And just to see the pattern, I'll go out one more term. It'll be minus x to the 6th over 6 factorial plus all the others. Plus I x over 1 factorial minus I x cubed over 3 factorial. Why? Because I cubed is minus I. And then I to the 5th was back to I, so that's plus I x to the 5th over 5 factorial. I was going to do one more. Minus I x to the 7th over 7 factorial plus dot dot dot. But what is this series right here? This is simply the series, the sum from k equals 0 to infinity of negative 1 to the k, x to the 2k, all over 2k factorial, right? Because it's the terms alternate by sign. So depending on whether k is even or odd, it's either going to be positive or negative. So that's what that does. I only want even powers of x, so that's why it's to the 2k. And I only want even factorials in the denominator. We okay? Okay. Have you guys seen this before? Some of you have? All of you have. I'm sorry, we'll get through it then. Plus I sum k equals 0 to infinity minus 1 to the k x to the 2k plus 1 all over 2k plus 1 factorial. And then as we said, well, that's the power series expansion. Oops, that's the power series form of the cosine of x plus I of sine of x. So at long last, we've shown that e to the I x is equal to the cosine of x plus I sine x. Okay. So, yeah.
And the I gets tacked on because the sine function is odd.
No, great question. No, it's not tacked on. I didn't show that. Sorry, I should have said this. Notice every single term in here has an I. So what could I do? I could take a line to factor all those i's out. Once I've done that, what remains? This power series. So I guess you could say the i's are there because it's odd, because it's all odd powers of i's don't vanish. But no, there's no, I mean, this is all straight up factoring things out and just rearranging them into the correct series. It's really kind of neat, right? I mean, to be able to get down into the inner workings of e to the x and show that it's got sine of x and cosine of x inside of it. Yeah. Okay. So just what have we said? So if I have an expression like e to the alpha plus beta I x, I could rewrite this as e to the alpha x times e to the beta I x. Let's let me write that as I beta x, which could be written then as e to the alpha x times the cosine of beta x
Sine.
plus I sine beta x.
Isn't sine the even function though?
No, sine is odd. Yeah, so one way to see that sine is odd is literally, and kind of justifies the word that we've always been using. The power series representation for sine has only odd degree polynomials. And so you could see that, right at the heart, if you put in a negative x, you can always factor a negative out of that. Yeah, great question. Okay, so we have this result, and I'm almost out of time, so we'll just cut to the chase. It's actually quite a bit of algebra to talk about how you can get rid of that I. Okay. What you have to do is make a couple of different linear combinations. So we just said that y1 equals e to the alpha x cosine beta x plus I sine beta x is one solution, and y2 equals e to the alpha x cosine beta x plus, excuse me, I want this to be the minus beta x plus I sine minus beta x. So if those are the roots to the, if r equals alpha plus minus beta x, then these are two solutions to the differential equation. But what's the rub? Why isn't that good? Why don't you want to give those as your two solutions? They look very similar to what I called the two solutions, but they're not. What's that?
Just because the sine cosine term is still imaginary? Or?
Yeah, we still have imaginary terms in that. I mean, that is a solution to the differential equation. You could take its first and second derivative, plug it into the differential equation, and show that it would work. But I really don't want to. And it's not very useful for then predicting, given a t-value, could you find the corresponding position of the spring, or whatever the differential equation is supposed to model. So that's not, although those are two solutions, and you could call them a basis, and you could say all solutions have that form, it's not very workable because it still has that I term. So I'm not going to do it because it takes about 10 more minutes and we're about out. But what we would do is we would say, okay, these two are solutions, but so is any linear combination of them. So I would start forming different linear combinations to make new solutions in such a way that I eventually get rid of, I eventually basically get rid of the i's, and then I just simply choose constants that get rid of a constant multiple that will get rid of the i's. Okay. So I'll just point that out. So we through a linear combination, we could say u1, or we could say u equals 2 e to the alpha x cosine beta x, and v equals 2i e to the alpha x sine beta x are also solutions. And then we multiply u by c1 over 2, an arbitrary constant over 2. That will give me c1 e to the alpha x cosine beta x. And we multiply v by c2 over 2i. That will cancel out the I. And because linear combinations of solutions are again solutions, scalar multiples of solutions are again solutions, that would give us those two separate solutions, giving the letters x equals c1 e to the alpha x cosine beta x, and x, that's x1, and x2 equals c2 e to the alpha x sine beta x, giving us those two solutions. So once we get to these two solutions, it's just doing some interesting linear combinations and then picking constants that get rid of i's, so then we've got those two solutions.
So you don't have to multiply both terms by the same linear combination. You can multiply by something entirely separate to get it a more workable.
Well, so remember, let's just say if y1 of t is a solution, so is 1 over 2i y1 of t. And that's not quite entirely clear. That, I mean, we've said a scalar multiple is again a solution, but it's not entirely clear that, we could use a complex scalar. Think of our vector spaces being over the complex numbers. Remember I said we had the underlying field? Usually we use R as our underlying field. But if we use C as our underlying field, then then we could pick 1 over 2i as a scalar multiple, multiply it to our solution, and it's again a solution. Yeah. The book decided not to talk about that, but anyway. Okay, so as a reminder,